Hello, good morning everyone. Welcome to the class ECE451, the control engineering. Today we will do a review for the last midterm exam. Alright, actually this midterm will just cover one chapter. Okay, ECE, turn around. 451. This is a 12th week Monday's class. It's a review. We do a review for midterm exam. This will be 3. Okay, midterm exam 3. For the exam, it will be on the Wednesday, the same week, right? 12th week, Wednesday, and during the class time. So that will be 9:30 to 10:45, and same way last time. We have 30 more minutes to prepare material to submit. So the whole exam time will be 9:30 to 11:15. All right. Okay. This is the exam time, and cover chapter 7, and totally will be 4 problems. Right. And similar, I suggest here you need to prepare a formula sheet. Right, prepare formula sheet. Actually, the exam, I don't restrict any material you want to use. You can use textbook, you can use notes, you can even search online, but that will cost time. So you prepare a formula sheet. This can save you time during the exam. All right. Okay, then let's go over. I put the textbook here. Alright, this is chapter 7. Chapter 7, the state space design. So we cover section 7.1, 2, 3, 4, then 5, 7.5, and find the controller, introduce the reference, input the way, force the feedback. Okay, yeah, we have this part. 7.5, then 7.6. Oh, I don't have 7.6. 7.6, no 7.6. No 7.6. Let me write it. Alright. We have 7.1, 2, 3, 4, 5, no 6. Then after 6, we should have estimator. Yeah, 7.7 estimator. 7.7 estimator. And 7.8 combine the controller and estimator. Right. We can use the output of an estimator and add a feedback based on that. Okay. And 7.9, no, we just have these. Okay, so we have sections 1, 2, 3, 4, 5, and 7 and 8 of chapter 7. Then we go over the topic we have learned. The first one, this is the start from, we can start from equation or transfer function. We start from a transfer function. Then we can have the matrix form, right? The state equation in matrix form. maybe you start from equation, same thing. Equation in of the just contain input output, right? Just contain input output, no state variables. So you start from this part. You can try to find the state equation in matrix form. And to do this, we have several different styles. We have CCF, OCF. These two are basically. And then we have MCF. MCF, it is not unique. CCF and OCF, they are uniquely determined. When you know the transfer function, you can almost write them directly. Right here, I do not repeat, but you should know how to write it. And MCF, you need to separate the transfer function into several parts. Then each part you can use either CCF or OCF. Then you can have MCF. This is one thing. Second thing is when you separate the transfer function as summation of several parts, but the summation you can put them in different order, then that will cause the matrix looks different. Right? And also when you separate the transfer function into different parts, you have more than one way to separate them. Right? So MCF, you can have a lot of different choice. If you need to solve a problem, you find the MCF. You can find any one, that will be fine. The result is not unique. You find one, that will be fine. Okay. So this is the first topic. Secondly, we need a transfer between different state equations. Right, different state equation. So we can start like x dot equal to ax plus bu, y equal to cx plus du. We start from this one. We want to find CCF. We want to find OCF. Right, we can have these two. This one you need a matrix P. The transfer, right? The transfer matrix P, there will be C times that M, right? Yeah, you should know what is M, all right? And this one, I use another P, I say Q, which will be M with a transpose times O, then with inverse. Here's the inverse of transpose. Sorry, I forget. This part is M inverse of M transpose. You check the notes. Okay, I have that in the notes. You check this part. Okay. Yeah. So, given any kind of system with a state form, with metric form, you can transfer it to a CCF or a OCF by a linear. This is a transform. We call this a similarity transform. Right? X equal to X bar. P times X bar. We use these as a transform. Right? Okay. This is from arbitrary to CCF or OCF. Then how about MCF? For MCF, you can consider this as an arbitrary one. Then we can transfer it to OCF or CCF. Right? We can do this. Right. Similar with that. This, I put the wrong order. Different. This is it doesn't matter. You can change to this one or this one. Right. You can find the matrix to transfer MCF to this or this. You buy some P or some Q. You can get this one. Right. This is a X equal to PX bar. This is a X equal to Q X bar, and you get this form. And then you use same P, same Q, then you consider this one go to a MCF by X. Okay, I suppose the state variable here is just X bar. If this is X, original here is X, then here will be X. X equal to, this is a P inverse times the state variable for this. I use X hat for it. Okay, and OCF also can go back to MCF by x bar equal to this Q, now is Q inverse times x hat. Right. This side here is AX, x dot equal to AX plus BU, y equal to CX plus DU, and this part, this two, there will be x bar dot equal to AX bar plus BU, and y equal to CX bar plus DU. And this one. And this one, there will be a x hat dot equal to AX hat plus BU, and y equal to CX hat plus DU. Like this. And different A. This A is original A. This is after some change. Okay. And this is you change it back. So this one is same with this one, but this is different. All right. Yeah. So you can change from any kind of system to this one, and if this one is a MCF, you can go to OCF or CCF, and then from OCF CCF you can go back to MCF. Right. Okay. Now I will see if I want anyone go to MCF, how to do it. You can think like this. You know how to transfer this one to CCF. Then from CCF, by this way, you can know a CCF how to go to MCF. Right. So I say this is 1, this is 2. So arbitrary x dot equal to AX plus BU, y equal to CX plus DU, arbitrary 1 by 1 to a CCF. Then by 2, where's the 2 coming from? This is 2, right? 2, you need this one. So suppose this is 3. So you find the MCF here. Then this one, this is a 3. And this is a 2. 2 is just a 3 inverse. Okay. So you find 3 firstly. From MCF to CCF, you have a P. You P do the transfer, you get CCF. Now use P inverse, you go from CCF to here. Okay, now you combine by 1, then followed by 2, you have MCF. You start from any arbitrary system, you can have a MCF. Alright. Okay. So this is a second problem, how to transfer from different kind of matrix form system to another matrix form system. Then the third one, we want to solve the system. Solve the system. I don't need this. Okay, I need to write this. Third one is solve the system. Solve the system. Suppose the input is given, then what are the state variables, state x, and what are the y, right? So we have these x of t will equal to a phi of t times x of 0. Here phi of t is an inverse Laplace transform of si minus a with inverse. Okay, this is phi of t. Then x of t will be phi of t times x0 plus integral. Okay, I just write as a convolution. It will be phi of t times b convolution with u of t. This one should be a matrix. Phi of t should be a matrix times b. You have a column vector. Then convolution with u means every element of this column convolution with u of t. Alright, this is x. And y it is just cx plus du. Now you plug in, you have c times phi of t times x of 0 and plus c times phi of t times b convolution with u and plus d times u. Sorry. Right, so we have this one. And then in the S domain, we can have the transfer function y over u. This will be c times si minus a inverse times b plus d. It's just this one. C times this in S domain is this one, right? And times b. This will be convolution with u, right? So this part is just the impulse response, right? Impulse response, convolution with the input, you get output, right? Oh, you still have this one. Okay, yeah, something like that. Then plus d. D is here. Now we have transfer function like this. Actually, this one you need this one in the previous step. In this part, when you try to find this P and Q, you need a matrix M, and then that M you need the transfer function. You need the denominator of the transfer function. Remember? And what is the denominator of the transfer function? It's just this one coming from this inverse. So it is we say the characteristic polynomial that is a determinant of Si minus A. This one will be the denominator, right? When you calculate the inverse, you need to put this in denominator. So this one is the denominator of this transfer function. Denominator of the transfer function. Actually, we have a formula. This one will equal to determinant of Si minus A, and here is also a determinant of some kind of a matrix. Yeah, I can't remember. You can check textbook. They should have that formula. But this formula is not so convenient. You calculate by this way. At least I think this one you calculate by this way is better than this one. You need a less calculation in this one. Alright, so remember this will be fine. Okay, this is how to solve the system. The important formula is here, this here. And do you know how to use it? I think we have a homework problem, right? You try to find the phi of t firstly. Phi of t. Then you need to calculate phi of t times x0, phi of t times b, and then c times phi of t times x0, then c times phi of t times b, then convolution of these, then add them together, you have y. You have output. The convolution you can work either in the time domain, that will be integral, right? Integration, you just by definition of the convolution. If you forget that part, you need to check the textbook. I think in the appendix they should have details, or even just search online. You can see what is the convolution for continuous time. Okay, and you can also send these to S domain by Laplace transform. It will be multiplication of Laplace transform of both time in the S domain. Then you go back. Use inverse, you can go back, right? So this part, it is C times Si minus A inverse times B and times U of S, right? It is this one. Then perform the inverse Laplace transform. Then you have this part, right? You just use the inverse Laplace transform. You calculate this one. It is just this convolution. Okay, this is the third part. Then the fourth, we need to do some calculations. The first one is about the steady state. Steady state. How to find the steady state? The basic feature is x dot equal to 0. So in the system, you will have some system. This one, or maybe you need a feedback, right? Depending on the system structure. When you want to find the steady state, the derivative should be 0. Then you can solve what are these x, what are these y. These are the value of the steady state values. And of course u must be step response, step input, unit step. Right? The input is unit step. Then this one is 0, you can solve it. Now maybe you need to add more equations depending on the system, depending on the problem. But the key to solve these kind of problem is derivative is 0. Steady state derivative is 0. Okay. Alright, this is a fourth. Then the fifth, this is a full state feedback. Now we have system look like this: x dot equal to ax plus bu, y equal to cx plus du. This part, this is a plan. Right, this is plan. Then we add the feedback r equal to u minus kx. So this is a full state feedback. Alright, full state feedback. You can see you have r. Here's a negative k. Right, this is x coming, and with x come out here from the plant. This is a plant. This is plant. Here's y. Here will be x dot of t. Okay, the plant u, sorry, u of t. Yeah, x dot will be inside u of t. So u of t as input to the plant. The plant will give output y of t. And of course, here for the full state feedback, we just need x. We do not use y. We use x to give the feedback. Right? So this is full state feedback. Then select. We can select k so that the overall system, the overall closed loop system. This system has poles P, which is pole 1, pole 2 to pole n. Now we can have these poles. This one given by you, choose by you. You can choose any kind of poles. Then you can always find the k. Make the whole system use these poles. Right, we have a formula. What is k? K is that function acre with a, with b, and with this p as input of this function. Then this function will return what is k to you. It's a MATLAB command. If you want, you can also calculate by hand. It will be this one, this c, and here will be a polynomial. It's a r of a, alpha of a, capital A of a, like this. Right? You can also have this. And what is a? That depending on the where a of s equal to s minus pole 1 times s minus pole 2 times until s times pole n equal to this. And you replace s by a, then you have this one. Right. And c. Did I mention what is c? Yeah, for CCF we also need this c, right? C, I need this is b, a times b until a n minus 1 times b, right? We have this one. So this is a full state feedback. What is feedback and how to choose k? Right? What is feedback? This is feedback, right? We use this as feedback. And how to choose k? We can use this formula. You can put the poles to any location, any location. Okay, this is a 5. Then the 6th one. Okay, that is a feedback. This one will be the estimator. Estimator. We have x dot equal to ax plus bu and y equal to cx plus du. This is a given system, right? This is the plan. Then we will build another system. It is just something same. You can think it's the same thing, but this one you build the one, it is totally open to you, and this one is closed to you. You cannot see what is your x. You can only know what is the input, what is the output. You do not know what is x. And you build another one, you can know everything inside this part. Okay, that is I use x bar take dot equal to ax bar plus bu and y bar equal to cx bar plus du. Okay, we have this. So this system, this part we use same u as input, and I have a state variable x bar, and it will return output. This is y bar, and we will check whether this work well. I need to compare this y and y bar. So and use y minus y bar as a feedback to this estimator. So I need a plus L times y minus y bar. Add this one. By add this one, okay. Then we have this part is estimator. And this estimator, that means x bar will close to x when t go to larger than 1. I write this way: t larger than 1. That means t large enough. When t large enough, these two they will be closed. Okay, so this is estimator. For this estimator, you need to choose L. Now how to choose L? So that we say that is the arrow pole. Arrow poles satisfy your requirement. It could be anything. Depend. Suppose these arrow poles, they are pole 1 to pole n. The arrow will be 0, 0, 1 times. Now I need O. I use O. Not this one. I can't remember this. I write this one. L will be the acre function. Use A transpose and C. Now this is C. I use this C. Here you use C with a transpose, and then here this is a P. This one. And after you calculate this one, you give another prime, another transpose. So error is this one. You use this to calculate the error. Alright. You can set the arrow has pole anywhere. Of course you can put this in the left half plane, so the whole system will converge. If you want to check the law, you can use the first one minus the third one. You will have x minus x bar equal to A times x minus x bar. This one cancel, and minus L times y, this part. And y minus y bar, you have C of x minus x bar. Then you can have a relation, you will have x minus x bar dot will equal to A minus LC times x minus x bar. So you have this, right? So you set the arrow pole are pole of this one. So arrow poles, they are poles of SI minus A minus LC with inverse. Poles of these. Or you say they are roots of determinant of Si minus A. Actually, I removed this out. There will be plus LC, right? The roots of these, or the poles of these. Yeah, this is a fraction. This is just a polynomial. Okay, so this is about the estimator. The basic thing is how to find this L. Then in the sixth part, actually we need the controllability. If the system is controllable, you can do this kind of work. Actually, in this Ecker, you need to use that matrix O, inverse of that O. And here you need an inverse of C. So we have more discussion on the controllable, and I say this is seventh, the condition of controllable and observable. Basically, we say this one controllable according to that C, the determinant of this is not 0, and observable related with determinant of the matrix O. Is it O? Is it look like O? Determinant of O. Okay, this looks more better like O, right? This one do not equal to 0. And O will be CA until C times A to n minus 1. This is O. And C I gave you before, right? Okay, so this is seventh part. Sometimes if we have more general case, if you have multiple input, you have to consider multiple input, multiple output system. You can still use this way, but you need to use not the determinant. You need the rank of C will equal to n. You need this one, and this is also rank of O equal to n. So you need this. Okay, then we have A's. I think I have another one. A's. What is that? Oh, reduced. Reduce the reduce the estimator. Reduce the dimensional estimator, right? Reduce the state estimator. Estimator. This is a case if I put y, it is just I have x dot equal to ax plus bu, then I put y, it is just one of the x. You can also write as 1, 0, 2, 0. Here's xa and all the rest xb, like this one. In this case, then in this case, how to give an estimator? We can reduce the dimensional of the estimator, right? You can have suppose this is a plant, this is the plant. Then you have output is y. Actually, y is just as same as xa. Then you can decide what will be u. You use u. You need two functions here. I can't remember. Should be two functions here. And then you do a summation. Here you have 1 over s. Suppose this is a z. This is another z. And this z plus L here. This is L here. Y times L times y. You do a summation here. Then this will be x hat, which is a estimator of xb. This part, xb. And this one go back. Here will be something like this. Here's a summation. Yeah, I think this will be a. or not 8, something. Yeah, here will be something. These 3, you check my notes or check textbook, you can find these 3. Yeah, so whole the reduced state estimator will be look like this. You only need to estimate this one. This is a one-dimensional less than the whole state. Now this one state is x. Suppose this, for example, this is a 4-dimensional, right? This part you only need a 3-dimension. Okay. And actually we have one more thing, but I don't think I have homework for that. That is, you combine 2 together. You use estimator. Then the estimator, you have x hat, so like this one. Then you use this one times a k as a whole feedback. Right? Yeah. Okay, that's all of this chapter. How many times? I only need 35 minutes. I only use 35 minutes. Okay. I will say if you have any question we can discuss, but not right now. Now I'm record this video, right? And then when you watch, suppose you are doing the class, so after you finish this, then you can go to the Zoom meeting. I will be in the Zoom meeting. So you have any problem, we can discuss there. All right. This is okay. Then see you later. Okay, maybe see you soon. Not see you soon. Now I'm few days earlier than the class time. But during the class time, when you watch this one, when you are done, if you have a problem, we can meet. Just you go to the Zoom meeting. All right. Okay. Then bye bye.